So good morning. Today looks like November 18th, and it's just before Thanksgiving. We have like 2 more classes, and then it's Thanksgiving break. Can't wait. So what we're going to do today is we're going to do lecture 19. Lecture 19. You got a couple? Yeah. Okay. Let me shut off the camera only so I can capture. The battery doesn't die. What we're going to do today is we're going to do lecture 19, which is omitted variables case. And as I said before, omitted variables are important first because they're on the final exam, and all of you want to do well on the final exam, I assume. And second, because you need to do an omitted variable example for project part B using the data that we gave you. And I was walking into class today and I was like, you know, not everybody gets omitted variables, but maybe I can give a couple more examples so that everyone goes, ah, I know what's going on. How many of you saw the movie Knives Out? What's Knives Out? It's pretty much a standard, murder mystery, right? And if you've seen, whether you've seen Knives Out or not, the standard murder mystery is like this. Someone dies early on in the movie, and everyone wants to blame somebody, usually the butler. But in this case, it wasn't the butler, it was the home health aide, the nurse, right? And then what happens? As the movie unfolds, someone says, we seem to have omitted some important information. And while it looks like the person is really guilty in the beginning, as more and more omitted information shows up, the answer switches. And that's just what happens with omitted variables in regressions. Oftentimes, if you're missing an important factor, things that look negative become positive, or things that look positive become negative. It's the same thing as these murder mysteries. And at the very end of the movie, what happened in Knives Out? Well, we probably shouldn't say because not everyone's seen the movie. But in almost all murder mysteries, what happens? The person who is suspected at the very beginning is typically innocent. And we have a reversal of the sign and magnitude. Make sense? Who is it? Was it Captain America in Knives Out? All I know is my wife was like, oh, he looks so hot in that cable knit sweater. I'm like, shut up, dear. Sorry, I'm on recording. Let's not talk about these kind of things. All right. Yes, and my response was, but can he act? Her response was, does it matter? Okay, so I'm going to go to our class website. And what lecture are we doing right now? We're doing lecture 19, omitted variables case. And what data file do we need, since this is QM222 and every lecture pretty much has a data file? So under data files, I remember to move it to the top. It's handout 15, pay for performance. Handout 15, pay for performance. So let me switch to the PowerPoint. And before we start today's lecture, if you actually read Project Part B's instructions, it says, please format your regression table. How do you format your regression table? Any of you actually read the textbook? I know it's free. I know it's online. Have anyone seen it? One person's seen the textbook. All right, 2 people have seen the textbook. That's pretty good. So out of those people who've seen the textbook, there is a chapter 22. It's at the very end of the book. And chapter 22 talks about formatting a regression table. It's a really short chapter. I think it's 3 pages long. Maybe it's 2.5, something like that. And in general, the way we format regression tables is we create a column. We put the coefficient and some stars. Stars typically mean whether something is significant and at what level. The normal number of stars, 90% significance is 1 star, 95 is 2 stars, and 99 or higher are 3 stars. It's the normal way. You put the standard error under it in parentheses, in parentheses. And then down the very bottom, you put the number of observations, the standard error of the equation. So when we make a prediction, what's the standard error? When we make a prediction, we can figure out the upper and lower 95%. And then you put the adjusted R square or the R square down the very bottom. And why do we do it this way? We do it this way so we can cram more information, more regressions into a regression table instead of just cutting and pasting from Excel. So cutting and pasting from Excel is okay, but it basically says, I don't really know what I'm doing. I'm a beginner at doing regressions. And if you format it the way chapter 22 set up, you can get, 4, 5, maybe even 6 regressions into a table. The other advantage of doing it this way is when you start adding more variables to the regression. So this is an example that talks about, I believe, number of medals won in the Olympics. And they have one variable which says, is the country having civil unrest? So are people fighting? Think about like Azerbaijan and Armenia right now. If you have civil unrest, the first regression says, oh, it's really negative impact on Olympic gold medals. And then they start adding in values like GDP, GDP squared, and you see we get omitted variables. The coefficient is -6 medals at the Olympics if it's just civil unrest, but if we take into account civil unrest and GDP, whether the country is rich or poor, we go from -6 medals to +1.5 medals. And then if we take into account a whole bunch of other factors like exports and so on, the coefficient drops to 0.6 medals. But what these 3 columns say is that there was omitted variables because just taking into account civil unrest didn't help. Does that make sense? And we can actually figure out if we have the background regression exactly how much. But right here we have the limited regression in column 1, and you can think of in column 2s, 3, and 4 as the full regressions. Right now we've only done one extra variable in the full regression, and that would be column 2. So we have columns 1 is the background. Sorry, let's try it again. Column 1 is the limited, column 2 is the full, and we're missing the background. And the background would be the relationship between civil unrest and GDP. Does that make sense? A little bit? All right, so let's go back to omitted variables. And I only mention this because some students, it's COVID, Thanksgiving, not a lot to do. So you may as well work on project B, which is due the Wednesday after Thanksgiving, maybe over Thanksgiving break. I mean, you might have something to do, but if you're kind of bored, project part B is a large part of your grade. As a quick refresher, this was the key equation from omitted variables. We had some combined effect, and the combined effect came from the limited regression, plus the direct effect, which came from the full model, plus the background coefficient from the background model, and then the coefficient on the second variable from the full model. And when you multiplied these 2 terms together, what you get is you get the amount of bias. And sometimes there's a lot of bias, and sometimes there's a little bit of bias. When we're watching murder mysteries, when everybody screams, the butler did it, and 50 people scream at once, and it turns out it's not the butler, there's a lot of bias. In murder mysteries, when people say it might be the butler, it could be the maid, it could be the cook, there's relatively little bias. It's just uncertain who did it. But when the entire world says that person did it, and it turns out it's wrong, then there's a lot of bias in the case. I don't know, does that make any sense?
Professor, I have a question.
Ashley, go for it. Nice to see you.
Just to clarify, so the bias term is like the numerical amount of bias, but then what does the combined effect exactly mean?
So going back one slide, the combined effect is -6.5. You're going to lose 6.5 medals. All right, that's the combined effect. And why is it called a combined effect? Because there's 2 effects. There's the true answer and the bias. And let's assume that we'll ignore columns 3 and 4. We'll just look at 2. There's some kind of bias here. So the first term, the direct effect right here is going to be 1.5 medals, and the bias is 5 medals. Actually, it's going to be 7 metals. It's going to be minus 7 metals. Okay. So what's going on here is the combined effect is this original term. The direct effect is the true answer. And the bias is how far we're off. Is that helping?
Okay, thank you. Yeah.
So I'm going to be quiet for a minute or two. And let's assume, since this was a final exam question, I think 5 years ago, let's assume that this is the same final exam question. It's not going to be on your test, but it'll be something similar. And it says, here are 3 regressions. Regression A is the limited, regression B is the full regression, and regression E is the background. The variable we're trying to explain is income. And we have 2 explanatory variables, gender, male or not male, and weekly hours, how many hours somebody works. Can you please calculate the direct effect and the bias? So the combined effect is pretty clear. The combined effect is $42,500. Can you calculate the direct effect and the bias? And I'm going to also explain, so if you're really fast at that, can you explain what all these coefficients tell us in simple words? I'll give you one more minute. All right, so here's what I'm about to say. I'm going to say what's on the next slide, if I can actually get there. All right. In general, being a male, the coefficient is $42,500. Annual income is the Y variable. So the constant says if you're not male in the first regression, if you're not male, you earn $101,000 annually. And if you're male, you earn an extra $42,500. In simple terms, it says from the first regression, and believe me, I have no idea where these data came from. I don't know if they're true or not. I don't think they're true, okay? It says men earn about $42,500 more than females in this particular data set. When we do the full regression, it says females, not males, male is 0, and weekly hours is 0. Women who don't work earn negative $26,000, which is a little weird. That means women who don't work, we take money away from them. So I'm not sure that really makes any sense at all. But it says after adjusting for weekly hours, men earned not 42,000, but 32,000. In simple terms, the bias is about $10,000 because we didn't take into account weekly hours. When we do the background regression and we have working hours as the Y variable and the X variable is gender, we get a coefficient of 3.6, 3.55 for those of you who like precision. 3.6 means in this data set, men work a little over 3.5 hours more per week than the typical woman. So if we match men and women up, men are working more hours in the labor force than women are. And because men are working more hours and many jobs pay hourly rates, there is a bias here. And that bias is about $10,000. So this number is a little too high. It shouldn't be 42, it should be less, $32,000. What does the 2,905, we'll call it $3,000, tell us in simple terms? For every additional hour you work each week, on average, you get about $3,000 per year. So wait, I work one more extra hour, I get $3,000? No. You work one extra hour per week, but that's 52 times a year. So basically you're working about 52 extra hours per year. For that 52 hours, you're going to get $3,000. This is a pretty interesting data set because that means people are being paid about $60 an hour, which is pretty high. Any questions about the coefficients before we jump into the bias term calculation? All right, let me go back one slide. The combined effect is C1. The direct effect is B1. The combined effect is going to be 42.5. B1 is going to be 32,194. A1 is the background coefficient. That's going to be 3.6. It's going to be this number down here. And B2 is the coefficient on X2, and that's going to be the $3,000. That's going to be the 2,905 right here. Does everyone see all the things line up? So there we're saying it again. I'm rounding slightly here. C1, 42.5, B1, 32, A1, the 3.6, and the B2, 3,000. The bias is about $10,000. Okay? Multiplying 3.5 and 2,905, the bias is $10,000. So we're overestimating because it's a positive coefficient. We're overestimating. Let me stop and ask, are there any questions? Does that make sense? Kuncha.
Yeah, I just want to ask, how do we know that the C1 is 42,502 by looking at the table?
We know it because what we're looking at is the limited. It's always the non-constant, and the limit just has like one variable. So
okay, A1 is limited and B1 is the full regression?
It is. A is the, so it says up here, A is limited, B is full.
Okay, yeah, thank you.
And even if it doesn't say that at the top, and I can't tell you exactly how I'll word the final exam question, but you know it's limited because it's asking about annual income. We have two regressions. One has more dependent variables than the other. The one with fewer is the limited. The one with more is always the full. And it's full because there's lots of stuff there. It's full. Limited means doesn't have very much stuff.
Okay,
Right.
makes sense.
Actually, I figured it out. Thank you. Sorry.
Great. So to go back, bias is about $10,000. We're off by about $10,000 because we're not taking into account hours of work, and there's a big difference between men and women in hours of work in this particular data set. By the way, I don't think this particular data set is true. Go ahead, Serenity.
I'm actually just going to ask to make sure, but to get 10,312, did you subtract C1 from B1? Or is there like more math that I'm missing?
No, we can subtract C1 and B1. So if we just have this, and we just have this, we can figure out the bias by subtraction, the total bias. But sometimes, Serenity, professors are nasty on final exams, and they might give you things like this number, these two numbers. I'm sorry, it's a little hard. Go away. Not you, Serenity, the keyboard. So it's an equation. So we could have, for example, the A1, the B2 term, and the C1 term, and ask you what's the B1 regression coefficient.
Oh, you're just asking. Okay, so you would ask us for the missing term out of that equation.
We can figure out the missing term. Yes.
Got
If you
you.
have
Okay.
all four coefficients, then it's pretty easy. We can just subtract the two and say, oh, this is the bias. But sometimes
Okay,
you don't
thank
have
you.
things. Sometimes you only know the background regression and the limited, for example. So this is handout 15. And the question is, should we pay high school students or junior high students to get good grades? Let me just ask you a real quick question. In non-COVID times, I usually send people off and to ask their neighbor, breakout rooms, things like that, but we'll just do a quick raise of hands. I'm an economist, and economists believe that incentives matter. And one of the strongest incentives is money. The problem is that not all students in junior high and high school take high school or junior high seriously. So is there any way we can get them to take things seriously? And a bunch of economists, particularly a group in Chicago, at the University of Chicago, wanted to reward students. Basically, well-to-do parents typically reward their children with money if they get a good report card. And I've even heard things of, really rich parents saying, look, you do something really spectacular and you can have like a car of your own. Like get all A's. And no, you've never heard of that, Sam? Okay. So this is the question. Sam's like, I just don't agree with that. So here's the question. Do you agree with bribing kids to get better grades in school? Yes or no? That's the question. So I agree with bribing kids. Please either raise your blue hand or raise your hand here in class. So I agree. I think bribing kids is an effective way of getting them to get like A's and B's or something like that. So right now, 5, 6 online, 7, 8, 9 out of 32. And how about in class? I think that's Isabel. Is that Isabel way up there? Yes. So we have one maybe, but she's raising her hand and begins with a J, right? Jacob. Well, at least I got the first letter right. So Jacob is a yes. So we have a yes and a maybe, and everybody else in class, I'm looking at 5 other people, 6 other people going, nah, no way. Okay, so we have 11, we have 1/3. Great, thank you very much. Should schools do this? What I want to do is I want to show you real quick at least one video on YouTube. It's 3 minutes long on the top one. And then the second video, I don't know if we'll have enough time. And then I want actually to bring up a data set. Go ahead, Stephen.
Oh, I don't have any question. This is for the previous raise hand.
Oh, okay, no problem. So I'm going to bring up this YouTube video. It's 3 minutes long, and there's probably a 10-second commercial ahead of it. At least it is at my house. Yep. All right, so share screen. Did that convince you in any way, shape, or form? Maybe, maybe not. So what I'd like you to do is open up that data file, which I believe is called Handout 15. Pay for performance. And let me share a different screen. Hopefully now you're looking back at the PowerPoint. Let me know if you're not. So they did these experiments back in 2007 to 2009, and they conducted experiments in 4 public schools, in 4 different cities. And they were able to convince the government and private organizations, the University of Chicago, to give about $6 million to 38,000 students. It's a lot of money. And they did a lot of different schools. In New York City, they paid 4th and 7th graders for performance on 10 different tests. So you took a math test, you took a science test. In Chicago, they paid 9th graders for 5 weeks for grades in 5 core courses, basically English, math, and science. Dallas, they were paying 2nd graders $2 a book, and they had to pass a short quiz to prove they read a book. They couldn't just say, oh yeah, I read the book. And they said, well, what was in the book? And the student would go, I don't remember. So you actually had to show that you read the book and understood at least some of the core concepts. In Washington, D.C., they chose a whole bunch of wide things, including behavior and whether you wore your uniform to school or whether you get kicked out. So they were providing incentives that were much less academically focused and much more socially focused in Washington, D.C. And what they found, the real results, is that incentives for output did not increase any achievement. So basically what they did is when they looked at standardized tests, they found that if you paid kids to take standardized tests and do well on a standardized test, think SAT scores or PSAT, that it actually had a negative effect in some kids and only a tiny positive effect, but that positive effect wasn't statistically significant. In simple terms, paying kids on standardized tests was an absolute failure. And they did some research into why, and it turned out that when you paid kids to do well on the SAT or the PSAT, they all choked. They're like, oh my God, this is like, $100 if I do well. The pressure caused kids to not perform particularly well, made things worse. But incentives on inputs were much more encouraging. What does that mean? So when you paid kids to read books and actually make sure they read them, that really improved reading and other skills later on in high school and later on in grade school and high school. Paying students for attendance, wearing uniforms, turning in their homework also really boosted a whole bunch of other scores. So does paying kids to do things work? Not necessarily the way you think. If you make it low stakes, it seems to work. If you make it high stakes, get all A's in high school, your sophomore year, tends to backfire. So what we're going to do is we're going to look at some data, and these data are made up. These are not real world data. Let me say that again. These are not real world data. And some of the schools in the district that we're going to look at in this made up district use pay for performance, and some of the districts did not. All right. The school superintendent is hiring you to basically evaluate the program and say whether the program is successful at boosting test scores. So is the program successful at boosting test scores? And you get a data set, and the data set has 4 variables in it. It actually has a couple more columns. I think it has 6 columns. The one you really care about is called score. That's what the superintendent is paying you to analyze. Current scores. You also have whether they're in the pay program or not, or 1 means students in this school are getting money to perform, and if they don't perform, they don't get money. 0 means it's just a regular school. just like Sam over here would hope for, right? There's no pay. It's just they teach you the best of their ability. You learn to the best of your ability. It's a couple of other variables, old score and poverty rate. So we have 15 minutes. I don't know if we can actually do this in 15 minutes, but we'll try, okay? Your goal is to create a limited, full, and background regression. We'll skip poverty rate. We only have 15 minutes. So the limited would be score is the Y variable for the limited. Score is the limited Y. And in the pay program is the X. That's the limited. The full is score is the Y variable. Old score and pay program are the full. And the background is what's highlighted, the relationship between old score and pay. In simple terms, can you calculate the limited, and then can you calculate the bias on the limited coefficient? What was the limited again? Score was the Y and pay program was the X. So in the limited, it's the coefficient on pay program, where just pay program is the explanatory variable. Can you calculate the bias in that coefficient? I'll give you a few minutes head start, and I'll be quiet right now. Okay, we have 9 minutes left. And when I timed myself, it takes me about 9 minutes to do this. So what I've written down here on the screen is the 3 regressions we want to do. We want to do a limited, where score is the left Y variable, and pay program is the right-hand side, and that'll give us the C1 coefficient. The full regression, score is the left-hand side, and on the right-hand side, we have B1, the coefficient on pay program is B1, and on B2, it's the old score. And then the background is the old score is equal to some constant plus A1 times pay program. And I've done, while you were typing away, one quick thing. I moved score, I swapped the pay program column and the score column so I can do this just a little bit faster. So I'm gonna pick data, data analysis, regression, and the Y range is always gonna be score, so it's, well, excuse me, for the full and limited, it's always gonna be score, so it's the B column, and the X range is just gonna be the C column or the limited. We have some labels. Click OK. And what do we get? The key coefficient is in yellow. And this says kids in the pay program, or the, excuse me, let's try it again. The pay program causes kids to do worse. Their score is 5.7 points lower on average. So that's what I got from the limited program, the limited regression. Any questions? Maybe online? Are we okay? Great. Let's do the full. So the full is where we do the same regression. And we add in old score. So instead of the X range being the C column, it's now the C and the D column. We'll pick OK. And what we see in yellow is that the coefficient has changed dramatically. Instead of being negative about almost 6 points, it's now a positive almost 4 points. There's a swing of 10 points. And what does this say in yellow? The pay program causes kids to do better on standardized tests. On average, about 3.7 points better. The pay program works. What is the coefficient on old score? The 0.8 tell us? Anybody? Go ahead, Steve.
Every 1 point increase in the old score actually increased the new score by around 1 point, like 0.8. Like.
Yep, exactly. So kids who do better before they implemented the program are going to do better in the future. Not as much, but kids who tested well earlier are testing well now. Now let's run the background regression, which is oftentimes the hardest to interpret. And what we want is we want old score as the Y variable. Old score is the Y variable, and the new variable, so Y is D1. And the X variable is going to be the pay program. C1 through C516, we'll pick OK. And what we see in yellow is we see minus 11 and a half. What does minus 11 and a half say? Sam? Yeah, places, for those of you who can't hear, Sam said the right answer. Places that implemented the pay program had much lower scores on the standardized test. They had 11.5, 11.4, 11.5 points lower than the places that didn't. So they seem to have implemented the pay program in underperforming schools, and in regular and high performing schools, they didn't implement the pay program. So the original, the limited regression was biased. Why was it biased? Because it was only done in low performing schools, which is why it appeared to have a negative effect. When you took into account how the school did before the program was implemented, it took into account all these problems. So we have 3 minutes left. I'll be quiet. We've now calculated C1. We've now calculated B1, B2, and A1. Can you create the bias equation? Can you create the bias equation and calculate the total bias? Okay, I only have 1 minute left, so let's do it right now together. What's the bias? The bias is C1 is equal to B1 plus A1 times B2. C1 comes from the limited, so C1 is minus 5.7. We'll jump back here. So it's minus 5.7, and that's going to be equal to B1 B1 comes from the full. B1 is 3.7. Plus A1. A1 is going to come from the background regression, minus 11.4. And we're going to multiply that by B2. And B2 comes from the full regression, which is 0.83. 0.83. So what's the bias? The bias is equal to K7, the minus 11, times M7. The bias is minus 9.5. We were underestimating by 9.5 points. It's now exactly 11 o'clock, and I want to leave you with one very important thought. That very important thought is the butler never did it. Thank you very much. I look forward to seeing all of you on Friday.
Thank you.
Professor?
Thank you.
Professor?
Go for it.
Could you please post this? I felt like it was kind of fast. I couldn't follow through it.
Say that again.
Could you post the Excel sheet
I will
of the work?
Excel sheet.
Yeah, thank you so much.
No problem. Save as to the desktop. What should we call it, Ashley? Handout 15
Like
solved. Solution.
yeah, that works.
Handout 15.
Thank you so much.
I had a question, Professor.
Go for it. Sounds like Serenity. Is that who I'm talking to?
Yeah, it is. And this might be a stupid question because I know it's from like 2 different units, but I'm kind of getting confused between like omitted variable bias and then like in situations where you told us to always get rid of one variable. Can you like just quickly differentiate when I'm doing the 2?
So when you get rid of one variable, that's when you're creating a series of dummy variables. And the examples I gave were like winter, spring, summer, and fall. So when I'm creating a whole series of related information that are all just dummy variables, I want to drop one because otherwise it's something called over-identification. However, the omitted variables is also, I accidentally dropped one, not I dropped one on purpose. So both of them have to do with dropping, which is why it's a little confusing in people's heads. Like, wait, I told you to drop one, and in the other case, I told you, no, you dropped accidentally one. So the idea is that with omitted variables, you accidentally dropped one, and you don't have over-identifying information, you have too little information. So here's the goal in life, Serenity. The goal in life is to have just the right amount of everything. You don't want to have too much of anything, and you don't want to have too little of anything. And omitted variables is basically saying we don't have enough. We need a little bit more. And when we drop one, when we're creating this sequence, when we have over-identified, we have too much. So both are trying to get you to sort of go sort of in this middle zone of the just right amount.
Okay. So then
the 3 bears story.
Okay.
Too little.
I think I understand that now.
Nah, listening to your tone of voice, I'd say maybe not. So should we try another?
No, I do also, but I have another thing that's kind of confusing. Like on the problem set, there's a question that asks to create variables.
Okay.
Do we learn that yet?
Create a variable. Okay, whenever we ask you to create a series of variables, you always have to drop one when you create a series. If you just create a single variable like on Beacon Street, you don't have to drop one. But if you create a whole series of variables that are all related to like location, let me say, so in the United States, we have the East Coast, we have the South, we have the Midwest, and we have the West Coast. So if we were to create 4 variables, East Coast, South, Midwest, and West Coast, we drop one. And why do we drop one? Because if I know that you're not on the West Coast, you're not in the South, and you're not in the Midwest, well, there's only one place for you left, and that's the East Coast. So that's a case of over-identifying information.
Okay, I'm good. Thank you.
All right, look forward to talking to you again. Who's next?
Professor, I had a quick question.
Sounds like good shot. It looks like good shot. Hello,
Yeah. For the background regression we did, how do we know what we put for X and Y? Like why did we have to put Y for old score and P program had to be X?
So there's a couple of different ways. One, mathematically, it's set up so you can just memorize which way it goes. All right. So
Yeah.
if you look at the equations that I gave you last time, B2 always goes in a particular slot. That's one way to understand it. The second way to understand it is even simpler than memorizing the exact order from the limited, and the background sheet, which, by the way, you don't have to memorize. You could, everyone gets a note sheet for the final exam. You just write down the equation and go, oh yeah, that's B2. It goes on this side. Okay, B2, A1 goes on that side. Just straightforward, plug and chunk. But pay for performance is a dummy variable. It's 0, 1. either the school was in the pay for performance program or not in the pay for performance program. And so far in this class, we've always put dummy variables on the right-hand side. We've never put dummy variables on the left so far. The last week of the class, middle of December, we'll do that. So since we've never put dummy variables on the left, we've always put dummy variables on the right. That's the fast way I remember it. It's like, oh, where's the dummy variable? Beacon Street or pay for performance. Ah, must be on the right-hand side. And the other X variable has to be on the left.
Okay. And if we did the other way around, this wouldn't make sense, right?
Right.
Okay. And like the first method you said, like B2 kind of thing, like, can you explain what you mean? I'm not sure.
I'm happy to answer questions, but I don't understand what your question is. So
Yeah, you were saying that there are two methods of like identifying. One is when it's a dummy variable. You just know that it goes to X because that's what we've done so far. But like there's another method of knowing it.
just look at the slides and just memorize it off the slide. So it's in slideshow 17. And it's slide number, give me 1 second here. Oh, not in the right directory. All right, slideshow 18, let me open it up. And then as soon as I open it up, I'll share the slide with you. Okay, so you just copy down this particular equation here. So x1 always goes on the right. It's the x variable, and the y variable is always x2.
Okay, yeah, thank you.
So you can memorize that equation there. X2 is always the left side. X1 is always the x or right side of the equation.
Yeah, got it. Thank you.
Okay. Serenity is still there, so let's chat a little bit more.
Yeah, I'm sorry. I guess I have a question going off of that. Like, you kind of told us what we needed to put in for the background. You said old score and program, and we kind of just had to figure out where to put it. Will you tell us, like, old score and program, paid program, like on like the final?
Nope.
No?
No.
So then, like, how I guess is that why we would like memorize where like the A2? Like, I'm not gonna, how would I know what to put for background if you didn't tell me that?
So the background comes from the explanatory variables in the full regression. The background is always looking at the two variables that are on the X side. So here, in the full model, and maybe this doesn't make any sense, but stop me if it doesn't. You have this full model. Y equals two things, X1 and X2. The background is always X1 and X2. The background always just compares these two variables in a regression. And the only question is, which goes on the left side of the equation down here, and which goes in the right? So on go ahead.
So you're given X1 and X2 in the full model, and that's how you find the background.
And on the final exam, you're going to be given three variables. I don't know what the three variables are, but we'll just use the same ones we just talked about, which will be test score, whether they're in a pay program, and their old test scores. And then I'm going to say what we really care about is current test scores. And if I tell you that, that means that's the Y variable, and the other two must be the X variable. Yes. So no, X1 in the limited is over here on the right hand side, and X1 in the background. They're both on the right side. So Y in the example we did in class was current test scores. And the X1 was, is it in the pay program? So down here, I'm sorry, the keyboard's not responding. Down here in X1 is the pay program, and X2 is this missing variable that we just added, which happens to be old test scores. So it's old test scores. The pay program is always on the X side. That swaps position. One time it's the second variable we introduce is one time on the X and one time on the Y. Swaps. It goes back and forth. I don't know, Serenity, if you're still there, does that help?
I couldn't really hear her, honestly.
Oh. So another way of thinking about it is that we have this limited model, which is current scores. I don't know if you can see my cursor squiggling around.
Yeah. Mm-hmm.
So current scores, and then are they in the pay program? Are they in the pay program always stays as the right-hand side of the equal sign. It's always on this side of the equal sign, okay? It's, are they in the pay program? Is there on the right side. It's here on the right side, and it's here on the right side. So the original variable that we're concerned about always stays on the right side. This X2 variable swaps sides. This new variable we're bringing in, which is the old scores. Okay, it was on the right side, and then it shows up on the left side of the background regression. So it flops sides from the right of the equal sign to the left of the equal sign.
Okay. Okay. I like halfway get what you're saying. I think that I just would need to do like an actual like example or review the one we just did to like understand how the variables are moving to each side of the equation, and then like figuring out which one I would put in the X and Y for the regression. But I like understand what you're saying.
All right, but let me be very clear. I want to chat with you if you don't get it before the final exam, okay? Because I want Serenity to get a high grade on the final.
You know, I want to get a high grade on the final too. So yeah, don't worry. We could do plenty of chatting till I figure this out.
Right.
But
You'd probably just wander over my office and sit there for 10 minutes, right?
if we were in person, you'd probably like need to put a sign that I'm banned from your office. Like I used to go to all my teachers' office hours in person, and like not even to talk about school, just because I like thought it was funny, and I wanted to talk to them outside of class.
No, I figured I'd see you a lot. I mean, there's certain students. I figured I'd see you and Steven. Are you still there?
Yeah, I'm still here.
Yeah, I figure I'd see Steven a lot too, and maybe Guncha. You know, the three of you would be like, you know, we'd be best bros.
Me and Guncha took 221 together, and we would always see each other in office hours.
Yeah. Well,
Yeah. Okay, I'm going to get coffee. Have a wonderful, wonderful afternoon. I'll see you on Friday.
okie dokie.
Thank you.
Bye bye.
Okay, go ahead, Steven.
No, you can go first.
Okay, just from what we were talking about, I just wanted to ask, so whatever we're trying to explain is the X variable, that's how it works, and is what we're always trying to explain a dummy variable type of thing? Like paid program is a yes or a no type of question? Or can it be like, I don't know, like can the old score, like where you can have any number be the X variable?
So I'm going to stop share for a second. I'm going to share a screen. So this is the lecture 19.
Yeah.
And here we had number of gold medals, maybe not gold medals, number of Olympic medals won. And we had here civil unrest, which is a dummy variable, okay, and GDP. So let's jump ahead. This model here, there's no dummy variables. So the one I had you calculate about an hour ago, no dummy variables at all.
Wait,
So
is male and a female, male or no male, and not a dummy variable?
You're right. I'm wrong. Sorry.
No, it's okay. So it can be. So we can have.
Yeah, sorry. I'll be honest. I was actually thinking of, there's multiple genders. There's male, female, there's non-binary. I was sorry. But in this, yes, in this example, it was just a dummy, 0, 1. Men and women. All right. Sorry.
No. But to answer my question, there can be cases where it's not a dummy variable.
Yes. There can be cases where it's not a dummy variable.
Okay, so it's just about like whatever we're trying to explain always goes into X.
No, whatever we're using as the explanation always goes into X. What we're trying to explain is always Y. We're trying to explain scores. We're trying to explain the house prices. We're trying to explain number of medals won. That's Y.
What about this pay program? Like, aren't we explaining the pay program itself? Like, does it work or not? And that's the X variable?
Yes, but what the superintendent cares about is not the pay program. What the superintendent cares about is test scores. That's what he or she is going to get fired for, or so they really care about test scores. The pay program is just a means to getting better test scores. So we're not trying to explain the pay program. We just say, is there a pay program or not? That's not explaining how it works or anything like that. We're trying to explain what causes test scores to go up and down.
Okay, so I think I get it. So what we're explaining in terms of like what variable? So in terms of whichever variable we're explaining, that's the X. Or like we're looking at the changes in the X. Like pay program is like we're trying to explain if test scores go up and down based on the pay program.
Yeah, based on the pay program.
Okay. Yeah, have a good day. Thank you so much.
Okay, bye.
Bye.
Hi, Professor. I just have a quick question about the background regression. So in the class example that we just did, the regression between pay program and O score, if I'm going to use one sentence to describe this regression, is that those school without a pay program, the score, the original score, the O score is like 11 points lower than the average.
Other way around, very close, except it was the other way around. Those schools with the pay program had 11-point less scores, lower scores.
Oh, so the intercept is when pay program is 0? No.
Let me share my screen.
Sure, thank you.
Come on, let me stop sharing. Sorry,
No, it's okay.
Let me try sharing again. So if pay program is 0,
Mm-hmm.
hang on, Kira, right? So Kira, can you tell us what these coefficients tell us in simple words? No, this is, yeah, the old score is the Y, and pay program is the X.
So without the pay program, the old school average 61.
Right, so without the pay program, schools without the pay program, I'm just repeating for Stephen, you're doing fine. The old school programs were 61, that's their number. Kids got a 61, a 62 on it. Right, so they put the pay program in schools that were underperforming. So in simple terms, the schools that had the pay program, their scores were about 50. And schools without the pay program, their old scores were about 62. I'm rounding slightly. Does that make sense, Stephen, if you were there?
Oh, I couldn't hear.
No, I repeated what she said. So what this says is the old scores, if you had no pay program is 0, no pay program, then the old score was about 62 in these schools. And if the pay program is put into a school, the old scores before anything was introduced, they were about 11 points lower, which means the scores were at 50 points. So
Oh,
schools that implemented
okay.
the pay program, their scores were 50 on this test. The schools that
Mhm.
didn't implement, their scores were 61.78, call it 62.
Oh, okay, okay. I got it. I got it. Now I got it. Sure. Yeah, thank you so much, Professor. I will review this example again to make sure I get it.
Okay,
Sure. Thank you so much, Professor. Have a good day.
nice seeing you.
Bye.